Okay, so I hope all of you are back. So we have so far discussed about the importance of electron microscopes. We have discussed about the historical developments about electron microscope, the need for electron microscope, how it is beneficial over an optical microscope, and what kind of information we can gather by using scanning electron microscope. We also learned some differences between transmission and scanning electron microscopes. We also learned about the basic parts of an electron microscope, and especially how they are organized in scanning electron microscope, and then how they each part function. So now let us discuss finally how the image is created in a scanning electron microscope. So this is how a scanning electron microscope actually looks like. You have the you have the electron beam column, and then you have the retractable sample stage at the bottom. This can be opened, sample can be loaded, and then various detectors sits above it. This is the EDS detector. So the image capturing in a scanning electron microscope, it happens because there is this scanning process. So while doing the scanning, you can think about it as it is like a digital camera. So a camera, when it has to capture various image from different places, so the camera has to move and focus towards a particular image. So this is the same way scanning electron microscope. You have a sample, you have the electron beam which is produced from the electron filament, and it passes through various lenses. These lenses focus your electron beam on your sample. You have scanning coils which moves your electron beam over the sample in a rastering fashion. So it is done by line. So when the electron beam is moving over each location on the sample, it dwells for a very small period of time at each pixel. So while during the dwelling period, signals are created from that particular place, and the signals are detected by the detector, and constantly the image is created. So if you have happen to see how the imaging is done in a scanning electron microscope, you will always see that the image becomes clear and clear from top to bottom in a linear fashion, because it is scanning over the sample in a linear fashion. So actually, the magnification in a scanning electron microscope is a factor of this, how much area being scanned to, the area of the, the console of the, your monitor. So, it is simply if an area of length L, small l, is being scanned, and when it is projected in the screen, so the capital L, the length of the screen divided by the length of the area that is being scanned, that gives you the magnification. So now we learned about there are two different types of detectors that we use in scanning electron microscopy. You have backscattered electron detector, and you have secondary electron detector. So, is there any difference in the information that you can gather from these two types of detectors? Yes. Actually, they are complementary, and they can be used especially for a composite material. So, for example, if you have a material, two or more different types of material present in the same sample. That is the case in mixtures and composites. So there, actually, depending upon, because backscattering depends on the atomic number. The heavier elements scatter more. So in that case, the contrast is better, in a composite or a mixture sample. The contrast between different elements are better in case of backscattered electron detectors, because due to the simple fact that the depth of penetration as well as the scattering is different, for elements of different atomic number. So the heavier elements will scatter more and hence so in this image, so in as well as the aluminum oxide in the background. So you can see that when you have a composite material with the elements having different atomic number, probably you can use backscattered electron detector for differentiating between materials in the sample. So finally, I would also like to say that this is how sample stage uh, this a sample stage look like. It is an aluminium stub on which you can load the sample. Typically, if it is a powder sample, you can can put the sample on top of it. But generally, what is done is, if it is a powder sample, because you are going to keep it under high vacuum, you have to stick your sample somehow. So it is done by sticking a carbon tape on top of your sample stage. So on top of the carbon tape, it is sticky. So your particles are deposited on the carbon tape, and then the imaging is done. So and additionally, when doing the imaging, you also need to remember that if your sample is conductive or semi-conductive, you can do the imaging directly. But if you have organic materials or biological samples which are non-conductive, then there is a possibility while your electron beam falls on it, the ionization will be more, and there will be charging of the sample, and your sample can get destroyed. So in order to avoid this, typically what is done is, after depositing the such samples which are non-conductive, a conductive coating is applied by sputter coating conductive elements such as carbon, chromium, or gold on top of your sample, and then the imaging is done. The coating is done uniformly over the sample by sputter coating it using a sputter coater, and then the imaging is done. Now, once as we learned about scanning electron microscopy, how does it function? So I will give you some examples of the application, because the applications are so wide and varied. So I can't give you exhaustive list of applications, but I will give you a glimpse. So we can study metals, metal oxides, semiconductors, ceramics, polymers, biological samples, bacteria, virus. All these can be imaged. Even I said, civil engineers do image, say, cement samples, or geologists study rocks, its composition, its its morphology, topography. So all these kind of things can be studied by using scanning electron microscopy. I will give you few examples. So in this case, say this is a nano composites of a conducting polymer and no metal, like platinum. So this nanocomposite has a different morphology. You can see in some cases it is spherical, some cases it is one dimensional. So your morphology of the nano material can be studied. So I am giving you the example of a nano composite here. So here I wanted to show you that. So although I said it's a nano composite of platinum and polyaniline, so I can't see the platinum here because the particle size are very small. So if you want to see the platinum in the nanocomposite, you cannot do it by using scanning electron microscopy. You have to use a transmission electron microscopy where the resolution is better. So I wanted to differentiate both. So here, similarly, say in this silver powder deposited on a glass substrate. So you can see three-dimensional image, including the glass substrate is visible. You can see that the spherical particles deposited on the glass substrate. You can do imaging like this. So if the morphology of the material is, if the material is having three-dimensional features, in this particular material you can see it's a rod-like structure, and the tip of the material is having it's like a pyramidal shape. So these kind of features can be studied by using scanning electron microscopy. This is, you can see the topography as well as morphology can be studied. So now, here again another example where the power of scanning electron microscopy and the complementarity between scanning and transmission electron microscopy. You might have heard about carbon nanotubes. They are very popular nanomaterials. The carbon nanotubes can be multi-walled and single-walled. So if you have a carbon nanotube, it is a tube. So the you can see the three-dimensional pore openings uh, of the tube in the scanning electron microscopy image. So you can actually see that it is a tube, whereas on the right hand side it is a transmission electron microscopy image. So here you can't say that there is a tube. Because the image is a two-dimensional image, it's a flattened image of the tube. So you can't say whether it is a tube or it's a wire. So, if you want to confirm that it's a tube, actually you have to do the scanning electron microscopy image. But then what is the difference? Say, if you want to differentiate between a single-walled carbon nanotube and a multi-walled carbon nanotube, so in that case, scanning electron microscope will not be able to differentiate that. So in that case, the TEM will be able to tell you how many walls, your material is a single walled carbon nanotube or a multi-walled carbon nanotube. So a lot of complementary information about the same material also can be derived by using SEM and TEM. So we have to make a judgment what information we are looking for, and then use the appropriate technique. So apart from studying the nanomaterials, even as I said, bulk materials also can be studied. Say, for example, failure modes in materials. This is a typical application for scanning electron microscopy. In this particular case, it is a space shuttle tile. A small portion has came off from the space shuttle, during the takeoff, and it is important to study, why the failure has happened. So in that case, you can see the, SEM is a very important tool for studying such application, because a composite can fail, say, if it is a delamination, if it's a bond between the matrix and the reinforcement, what is broken, or what has happened. So in that those kind of information we can study by using scanning electron microscope. So it's commonly used in study the failure modes, be it composites or metals. So I will giving you some unusual examples as well. So in this case, say for example, in museums, where the artifacts from ancient times are kept. So there again, you need to preserve them properly. If they are getting corroded, how the corrosion is happening. First, we need to study. Then only we can prevent it. So here again, scanning electron microscopy is a non-destructive technique because you can take a sample inside the SEM without destroying your sample. So that is, here in this case, it's a glass piece on which some corrosion layer is getting deposited. You can see, and then not only you can see that some deposition is getting formed, and what is the material? Say in the lower panel, it is antimony that is getting, deposited. So probably the material is, the antimony is getting, excluded from the material, and it is coming to the top and getting deposited. That's, so then once you know this, so you can take appropriate, precautionary measure to prevent such a thing. So not only in museums, so in order to study the fossils, in that case also, because SEM being a non-destructive technique, you can study, fossils, its features, what is the chemical composition, what is the microstructure. So those kind of things we can study in paleontology. Not only this, now very important application of scanning electron microscopy is in electronic fabrication. All your computers, mobile phones, and all your electronic devices work based on electronic fabrication, right? So in electronic fabrication, when the integrated chips are made, so in each stage, so you start with a silicon wafer, and on it you need to first apply a photoresist, then do the patterning. So once the patterning is done, so whether the pattern formed is uniform, it is appropriate, whether it is having defects, each stage of the electronic fabrication, actually SEM is a crucial technique for them, because each stage you need to monitor whether your IC fabrication is progressing as planned or not. So they use extensively, scanning electron microscopy in electronic fabrication. So apart from fabrication, imaging and analyzing materials, so scanning electron microscopes also can be used for doing patterning, even for fabrication. So this particular pattern is by using electron beam. So then it is called electron beam lithography. So this, the IIT Mandi emblem is created on a silicon wafer by using electron beam lithography in this particular case. So you not only can do the imaging, you can also do create patterns on substrates by using electron beam lithography. So far we discussed about scanning electron microscopy and its application in material science. So which is highly, which is the topic of today's discussion also. But apart from material science application, a lot of application is there in biology and biological materials. So in biological materials, when you do the imaging, as we know, scanning electron microscopy as well as transmission electron microscopy, it works under high vacuum conditions. So in those cases, there are certain limitations for biological samples. Say, for example, we know that cell contains a lot of water inside. So if you take the cell inside a high vacuum, it will burst. So your cell structure will be lost. So traditionally, so imaging using electron microscope of biological samples need extensive sample preparation. First, the sample has to be frozen and then preserved and then carefully do the imaging. But thankfully, with the advancement in scanning electron microscopy, now there are scanning electron microscopes which can work under different pressures. So these are called variable pressure scanning electron microscopes, or even there are some SEMs are called environmental SEMs. That means even if you have moisture inside the sample column, you can do the imaging. So this is especially important for biological samples. So in variable pressure electron microscopes, only the sample chamber is the pressure can be varied. The electron gun column will be still under high vacuum. So only in the sample chamber you can have ambient conditions, and then you can do the imaging. So interestingly, you can see you can even take live creatures inside the SEM and do the imaging. So here you can see the live centipede is taken inside a SEM, and then its image has been taken using scanning electron microscope. Lot of biological samples like bacteria, virus, even live cells. So all these pollen grains. So all these can be taken inside the scanning electron microscope chamber, and you can do the imaging. So very interestingly, it's not only possible to capture the three-dimensional image of biological objects, you can actually give false coloring. So in this case, you can see that this is a pest which affects the soybean plant. So it's a nematode. It's a worm, and with its egg. So in this case, false coloring has been done to actually create the live features. So this is also possible by using image processing softwares that are attached to scanning electron microscopy. So it is also used for a lot of biological application which is related to material science. Say, for example, there is a lot of materials, nano technology that exist in nature. By mimicking them, actually, we can create very interesting applications. So one example is this. This is a shrimp. It's a marine creature. It's a compound eye. It's having a compound eye. So the compound eye feature is captured by using scanning electron microscopy. So now if you mimic this, it's like this particular creature is able to view wide angles. It's almost 360-degree it can view, and even it can detect formics as a material. You can create sensors, or which can detect wide angles in 360-degree. So so with this, I will stop on the application of scanning electron microscope. I will now move on to the transmission electron microscope. I will try to discuss about the basic functioning of TEM, and we will also discuss about its applications. So as we discussed in the beginning, in TEM, it is the transmitter electrons which are captured. So the electrons which are passing through your sample, which then it forms a shadow of the sample, like before form shadow, or if you remember the old time overhead projectors. So there you have a printed sheet kept on a glass, and then that is illuminated from the bottom, and then projection can take place on a screen. So TEM is like a projection. You can capture only two-dimensional images by using TEM. So apart from imaging, so you cannot study the topography unlike in SEM. You can study the morphology to certain extent, not fully. Say for example, if your nanoparticle is uh, s- spherical, but it has some three-dimensional features. Say it has one side, if it is triangular or pyramidal. So those kind of features cannot be studied by TEM, but of course you can do such imaging using SEM. But you can of course do elemental analysis, you can do elemental mapping, and you can obtain crystallographic information from TEM. Apart from that, the resolution of the TEM is much higher than SCM, and so you can do elemental, even atomic imaging. Atomic resolution can be achieved by using TEM. So TM is also a powerful technique, but we understand the difference between TEM and SEM. So the parts of a TEM are similar to an SEM. You have an electron source which is sitting at the top, and then you have an electron beam column. You have a series of electromagnetic lenses, apertures, and then you have a detection. But the primary difference is, in SCM, your sample sits at the bottom, whereas in TEM, your sample is in between the column. So the sample is actually, inserted in the electron beam column in between. It's understandable because in SCM, it is the backscattered electron or the secondary electrons which are detected. But in tritium, it is the transmitted electrons. So your sample sits in the middle of the electron beam column. So electron beam is first falls on it, and then the transmitted electrons downwards is finally focused on a small screen, and then it's a fluorescent screen. You can either see the image directly, or you can capture it using a camera. So the so the TM, yes, the image is captured at the bottom because the sample sits in the middle of the electron beam column. So so this is so the parts are similar, but even the function of the parts are similar, but the organization of the parts is different. So here the sample, unlike in SEM where the sample sits at the bottom, in TM the sample sits in between, in the middle of the electron beam column, and the projection of the or the shadow of the sample forms on a small screen at the bottom, or you can remove that screen and then the camera directly captures. Camera sits at the bottom. So this is how a TEM functions. Well, so here I just wanted to show you. So it's so in TM the sample has to be very thin. So typically, unlike in SCM where the sample is loaded at the bottom, so in TM the sample is loaded onto a copper, grid on which the samples are deposited, very thin or very small size sample. So there is a lot of limitation of the use of sample in SCM, in TM. In SCM, you even if you have a piece of rock or if you have a live, a creature, you can take it inside this SCM chamber and do the imaging. But that is not possible in TM. Here, the sample has to be very thin and narrow, or a fine powder that is deposited on a small disc of copper, which is of course having mesh, typically 200 mesh or 300 mesh, and on which there is a small membrane will be there. So the particles get stuck onto the membrane, and then that is loaded onto the sample holder. It's a small cavity, and then this sample holder is inside, inserted into the column. So, depending upon the acceleration voltage that is used in TEM, so SCM, the maximum acceleration voltage is 30 kilo electron volt, and it can be lowered down to say 500 electron volts. But in TEM, it starts with say around the I think 3 kilo electron volts upwards, even up to say 300 kilo electron volts. So very high acceleration voltages are used in TEM. So that is why you get better resolution. And there are TMs which which varies in sizes. So when you have a 300 kV TM, actually, so this is a 200 kV TM that we have in IIT Mandi. It's a 200 kV TM, but you can have a 300 kV TM, which you can see, it's a double the size of a human being. So there are such gigantic TMs are also there. Well, when you increase the acceleration voltage, of course the column length increases. Of course, the resolution becomes much better. Atomic, resolution images can be easily captured with such high resolution TEMs. So, well, some of these I will skip now. uh, so in case of SCM, the backscattered and the secondary electron are used for creating the image. But in case of TM, the contrast is coming from two factors, because the electron beam is passing through your sample. So if your sample is dense, so then it will block more electrons, so the shadow will be darker. Similarly, if your sample is thicker, then the shadow will be dark. Uh, uh, so the contrast in TM is coming from both density as well as thickness. So in less dense and thin samples. So of course, like biological samples and so where the only carbon and hydrogen are present, or organic samples. Sometimes it's difficult to obtain the contrast using TEM. In those cases, actually, staining is done. Staining is done by using heavy elements like uranium, manganese, and osmium. The salts are deposited onto the sample, so a negative contrast is created in this fashion. So this just to give you an example, this is PMMA nanostructures. So the nano wires of PMMA has been created, but if you take try to do an image directly by using TEM, you will not be able to see the image clearly. So, but it is now negatively stained with heteropoly tungstic acid. So the heteropoly tungstic acid create the dark regions. So due to that, the lighter polymer nanostructures are visible. So, so apart from that, the electron scattering in the forward direction, a lot of electrons can pass through the sample without interacting, but electron also can scatter in the forward direction. The elastic scattering can take place apart from the backward direction. Elastic scattering can take place in the forward direction as well. So when electron scattering take place, so this information, means it is actually electron diffraction. So this electron diffraction in the forward direction actually can be used to study the patterns. The patterns that are formed by these scattered electrons, that depending upon the type of the pattern, you can determine the crystal structure. So if the scattered pattern is a random pattern, that means your material is an amorphous material. But if it is an ordered pattern, like you have an X-ray diffraction pattern, when there is a no specific pattern, then it is an amorphous material. But when you have regular patterns in electron diffraction, that means you have a crystalline material. And now, depending upon the type of patterns, you can further classify your material, whether it is a single crystalline material or a polycrystalline material. and you can also study identify the crystal structures. I will because due to the paucity of time, I will skip some of these slides. So a very important aspect I would like to mention here, in TEM your sample thickness, as the contrast is developed by density as well as thickness of the sample. So there is it's very important to have a sample of adequate thickness. So your sample should not be too thin. If the sample is too thin, there is no contrast. If the sample is too thick, then it's too much scattering. That means too much contrast. Your sample features will be lost. So a thumb rule is the thickness of the sample should be comparable to the mean free path of electrons in the material. So mean free path, we understand it is the distance, average distance traveled by electrons uh, you know average distance traveled between two collision events within a sample. So if the sample thickness is comparable to the mean free path of the material, then you get better image in TEM. So thickness of the sample, it's a very important aspect in TEM. So in TEM, there are few different imaging modes. One is a bright field mode, another is a dark field mode, and a diffraction mode. So what is the difference? So it depends, how, what information is used for constructing the image. Typically, it is the bright field imaging is what is done. So the transmitted electrons which are, going through the sample without getting scattered. So those electrons, if you capture and collect the image, so then it is called the bright field image. So in bright field image, it is the transmitted beam is used, for the constructing the image. But in dark field image, the transmitted electron off, and only the diffracted electrons are used for constructing the image. So this can be done in two ways. Either you insert a aperture so that the transmitted beam is cut off, and only the diffracted electrons are allowed to pass through, and then you construct the image. Or you need to tilt the electron beam and then align in such a fashion that your primary electron, the transmitted electrons are cut off. Anyway, so this is called off-axis imaging or tilted beam imaging. So, so bright field and dark field imaging actually gives you complementary information. Say this is an example. So this is an example of a bacteria where we have, means in this case, you have a dark field imaging and a bright field imaging. So areas which diffract more will appear as dark in bright field imaging, whereas it is the reverse. Areas which are scatter more will appear as light in case of your dark field imaging. So it can be used for getting complementary information of the same sample. You can take dark field as well as bright field imaging and study the complementary features in the sample. So now coming into the electron diffraction. So the electron diffraction also follow the Bragg's law. Bragg's law, I hope you remember, is the basis for the X-ray diffraction. So where the wavelength of the X-ray is related to the diffraction angle theta, and then depending upon the planes in the crystal planes in the sample, the diffraction will be different, and hence you can find out the d distance between the planes, that can be this obtained. So n lambda is equal to 2d sine theta. So this is the basic equation that is used in X-ray diffraction. So the same law applies in electron diffraction as well. So, depending upon the, as I mentioned in the beginning, depending upon the type of the pattern, we can identify the crystal structure. So, if the pattern that is formed is a random pattern, so then you have an amorphous sample. But if you have transmitted beam plus rings, a pattern having a transmitted beam with rings like this, you have then it is a polycrystalline sample. And if you have a transmitted beam with rings but bright spots, so then you have single crystal samples. So now distance between the center of the pattern and the rings or the spots, it is related to the different crystal planes. So this information can be calculated, and then you can identify the crystal planes present in the sample. How? This is the original, the actual electron diffraction patterns. We typically call it selective area electron diffraction patterns. So you see, in an amorphous sample, there is no definite pattern, whereas in crystalline samples, there are definite patterns. There are bright rings or bright spots, depending upon whether it is a single crystalline or polycrystalline. So, from the electron diffraction pattern, as I mentioned, you can find out the distance between the center of the spot and the each ring or spot. So that is called R. And then the distance between your sample and the camera is called the camera length, which is L. So R and L are related to the D, which is the unknown quantity in case of crystals. So the D, if you know the value of the D, you can identify the crystal plane. So RD is equal to lambda L. So when you calculate R, so you can calculate D, because L is a constant, lambda value we know, and then you can calculate D. So in this fashion, so by calculating the value of the D, we can identify the crystal planes that are present in your sample. So in this way, electron diffraction can be used to identify, the material, whether it is amorphous, crystalline. If it is crystalline, what are the crystal planes present in the material? So in this way, you can study the crystal structure. Now I will go through some application examples of application of TEM and SEM. To especially to highlight the usefulness of TEM. So TEM and SEM often are used to derive complementary informations. Say, for example, in this case, in the first image, it is an SEM image of a silica nanoparticle. So they are spherical particles, but this silica is a mesoporous material. That means it has a very narrow, nano-sized pores. So these pores cannot be viewed by using scanning electron microscope. So whereas if you take a TEM image, you see the fine narrow channels of the mesopores can be directly viewed by using TEM. Apart from that, so such porous materials are used as a catalyst support or adsorbent supports, where other materials like platinum nanoparticles are deposited. Again, if you take a SEM image of the platinum, nanoparticle supported silica, you can't see platinum because the size of the platinum is very small. Whereas when you take a TEM image of the same sample, you can see the fine platinum nanoparticles and the location whether it is present on the outer surface of your silica nanoparticles or even within the pores of the material. So this kind of information you can obtain by using TEM. And similarly, say for example, if there is a hollow material, again SCM can clearly tell you that it's a hollow material. Whereas if you take this image of the same material using TEM, it may not directly tell, but in this case, you can see when it is hollow, the outer edges are darker, and the center portion is lighter. From this, you can make a guess, but you cannot confirm it unless you do SCM. Similarly, when nanoparticles or any other material, this is a surfactant self-assembly on carbon nanotube. So, so this is done by cryo-TEM imaging. Of course, SCM will not be able to differentiate these patterns. So platinum nanoparticles supported on carbon nanotube. Again, the carbon nano, well, whether it is a tube or not, you cannot see from this image. You have to do an SCM, as I told already. But these fine nanoparticles uniformly supported on the carbon nanotube, which can be visible from TEM imaging. So now, when I mentioned about carbon nanotube, I said, well, three-dimensional pore openings can be viewed only in SCM like this. Here you can clearly see that it's a tube, whereas if it is a multi-walled carbon nanotube or a single-walled, you can't differentiate by using SCM. There are no signature here. Whereas when you take the image by using TEM, so the number of walls can be counted. You see, so each of these lines actually correspond to the number of walls in the multi-walled carbon nanotube. So in this way, not only you can identify whether it is a single walled or multi-walled, if it is multi-walled, how many walls are there? That also can be studied by using TEM imaging. So so similarly, I'm trying to contrast between the power of SCM and TEM. Say, so now you see this is a cubic sample, cubic nano-sized cube. So here this cube has fine edges, truncated edges. So these edges are visible, only in SCM image, because SCM give you a three-dimensional image. Whereas TEM, image in this, so it is not telling you about the, the truncated edges of the sample. So, so in this way, you can obtain complementary information from TEM and SCM. So there are other materials. Again, this is a two-dimensional palladium, nano sheet. So here again, the shape, the hexagonal shape of the palladium can be studied by both SCM and TEM. But apart from this, as I mentioned, the use of TEM is much more for studying the crystal structure. So because in high resolution TEM imaging, because of the resolution of the TEM can be as low as 0.1 nanometer. So in that case, you can create, so this is a tin oxide material where each of these dots that you see here, they are tin atoms, and so the position of each atom can be seen from the hello. Okay, no problem, no problem. I will wind up in another 5 to 10 minutes. Okay. Sorry for the interruption because it was Dr. Ashok Kumar who was calling me to tell that both the hosts are unable to connect because of the internet problem. Anyway, we will continue and try to finish as soon as possible. So what I am telling you is this: such high resolution images with positioning of each atoms are not possible in SCM. So this is only possible with TEM. Somebody is complaining about noise. I am not hearing any noise, but I don't know means why the participants are hearing noise. Unfortunately, I can't do anything because it's controlled by the host, and the hosts are unable to log in. So we have to bear with that. I'm sorry for that. So what I am telling is, so the power of TEM lies in such the ability to take such high resolution image with atomic resolution. So in this case, the crystal planes. I can't mute all the participants. So people are complaining about background noise. Unfortunately, I can't do this. Only the host, Dr. Ashok Kumar or Dr. Pankaj, they only can do that. Unfortunately, I can't do anything. Okay, so let us come back. So I can request all the participants to mute your mic yourself. Please do that because people are hearing a lot of noise. So I request all the participants, please ensure that your mic is muted. Please do that. Okay. So using TEM, we can study the lattice structure. Not only the lattice structure, what kind of crystal structure is present. You see the 101 plane, 010 plane, and then if there is a vacancy in the lattice, so if there is a defect in the lattice, all these things can be studied by using high resolution TEM. So TM also can be used for studying, say, composites of graphene. So in this case, it's a palladium nanoparticle supported on graphene. The palladium nanoparticle and its uniform distribution on graphene. Repeatedly people are, telling that there is a noise. Participants, please ensure that your mic is
उनकी वो टेक्स्ट वर्क की पिंग भेजनी थी, लिख के तो भेजी मैंने उनको फोटो। छुट्टी का काम देखिए, बहुत लंबा चौड़ा प्रोसेस है ना। नहीं डोमिनेट बैठे बैठे काफी सुबह से आए से लगेगा यार कंप्यूटर के ऊपर बैठे थोड़ी देर में निकलूंगा, अभी थोड़ा सा काम बाकी। इसमें लेट हो जाऊँ, आज 1 बजे तक नहीं पहुँचूँ क्योंकि थोड़ा सा काम जल्दी आगे निकलूंगा यहाँ से। जो तुम बताओ क्या बनानी है, आलू खराब तो नहीं हो रहा ना? एक बार देख लो, देख लो, काफी दिन हो गए आलू लाए हुए हैं तो जोलदार या तो देख लो एक बार हो। करनी चाहिए।
அது என்னன்னா இது என்ன பண்ணுது பஜ்ஜின்னு கலர்
Imaging. That is the confirmation whether it is a new virus. One of the very important things, in virology. All the participants, please mute yourself. A lot of people are making noise and talking. I request you to mute your mics. Now, but with the imaging of the biology, unlike in it, can't have stable pressure, in SCM, in TM. So typically you need to do some, bioprocessing. The sample has to be first, freezed using liquid ethane, and then further a lot of sample processing has to be done before the imaging can be done in TM. But nevertheless, it's highly useful. I will come to that later. So, apart from imaging, we can do elemental mapping. And, before concluding, I would like to say, although I consistently reviewed the three-dimensional image, well, the technology has proven me wrong. So the latest advancements, electron tomography, where actually it is like CD, it's and there, you two-dimensional images in pixels, then electrically with the help of softwares, image processing software, and stitch these three-dimensional images together, three-dimensional images. So in this way, using electron tomography, actually you can three-dimensional image EM, and this is, mind you, this is the most important for studying biological structures, actually protein folding, all this of, say DNA structures. This kind of structures is very important tool for studying that, this 3D tomography. So I have given a few examples. So by using, 3D, you can actually create three-dimensional images of biological structures and materials. I don't have much time to. So here you can see the three-dimensional image, of biological samples are possible by using. So actually, it's so important that the Nobel Prize in 2017 in chemistry was given to these three people, Jacques Dubochet, Joachim Frank, and Richard Henderson, for their contribution in the development of cryo-EM. None of them are chemists. Interestingly, actually, Jacques Dubochet actually is a biophysicist. So he developed this method for flash freezing biological samples. Actually, is a biophysicist again, and he developed the software for creating, images. And Richard Henderson is a molecular biologist. So all these three people have done extensive development in cryo-TM for biological samples. So in fact, it is supposed to be the next big thing, the cryo TEM for studying the biological sample. Doing imaging, you can do electron spectroscopy. You see, when your material has many elements, multiple elements, in this case copper and silver is present, where exactly is present, where exactly silver is present, it can be identified by using EDS mapping. Microscopy, which again is a powerful technique. So there are a lot more associated techniques. One example I would use electron energy loss spectroscopy. Actually identify frequencies in lattice of materials, which can also be used for imaging. With this, I would like to conclude that both these electron microscopic techniques with allied analytical techniques are powerful tools for characterization of material samples. Study the structure of the material, its composition, its crystal structure. So all these are very important aspects for the development of the material for various applications. So by studying the microstructure, you can understand the material and develop, its the properties can be tuned and new applications can be studied. So with this, I will conclude. I thank the organizers once again, and thank you all for your careful, participation. I'm apologetic for the noise towards the end. Unfortunately, both the organizers got locked out by the system due to the problem in their internet connectivity, and due to that, they could not mute all the participants. So anyway, I hope you could get at least some basic idea about electron microscopy and its power and its applications. So you are most welcome to contact me electronically if you have any questions. So if you have some quick questions, you can type in the chat box. I can answer right now. If not, we'll wind up.
Hello, is Dr. Felix?
Well, since there are no more questions, thank you all once again. Thank you very much.
डालना है वो बच्चे वालों की जो सिलेबस थे ना
मिठाई हम अभी खुद नहीं चाह रहे हैं कि सिर्फ मिठाई से अभी हम लोग तो मुर्गा का मिली